Hi, and welcome to Material Physics 6. This is a fairly short one to just round out the week, but what I wanted to really delve into is what is torque. So torque is whenever something is turning, it's that turning force. Now that's different to a force making something move. Yeah, so think about it. A car is driving along a flat road. It's got lots and lots of force pushing it forwards. It doesn't really have any torque because it's not turning. It then smacks into a log and starts jackknifing and flipping over and over. Now it's got torque because it's spinning, but it's still got that forward force, which is why it's moving forward. So we can separate out the turning forces, the torques, from the forces which are moving us through space. A torque just makes you spin on the spot, whereas a normal force, a sort of pushy force, means that you're going to move through things. Torque is a sort of force, but we can sort of separate them out just using language. I think linear force might be the more precise way of those other sorts of forces. So, torque, turning force. Now you've met turning forces before because we've done moments. Moments, I'm sure you're well aware, is just the force multiplied by the perpendicular distance to the pivot. So if we know this distance r and we know this force F, then we're off to the races. That gives us our turning force of a lever turning something. However, when you get to degree level, things are going to get a bit more mathematical. And this turns out to not really work for all sorts of reasons. So, how else can we define torque? Well, the first way is we can actually just define it off angular momentum. So torque is given a tau, which is just like a little t, and we can say torque is simply the rate of change of angular momentum with respect to time, dl by dt. So in exactly the same way that force is equal to the change in momentum with respect to time, torque is just how much the angular momentum is changing with respect to time. So that works really well. However, if we wanted to calculate it directly, because we didn't know the angular momentum and we just knew the forces involved, we've got a bit of an issue because this abstraction has two problems to it. The first is it's a perpendicular distance and the force has to be perpendicular to that, and that's the only way that equation works. And secondly, it's assuming that we're just keeping everything to one or two dimensions. Everything's in the same plane, nice and simple, but of course torques could be three-dimensional. The force could be a 3D vector coming into line which is three-dimensionally out from just a perpendicular. So how do you get around that? The answer is by using cross products. Now, this is something I know you've probably done at the end of your second year maths, especially you further mathematicians out there. It turns out if you take the cross product of the vector, which is your distance from the fulcrum to where the force is happening, and the vector of the force itself, because remember forces are always vector, they have direction. If you take the cross product of those two, that will give you your torque. Okay, nice and easy, but hopefully that's really got this idea really deeply in your brain. There's an interesting cross product question underneath. Have a good weekend. I'll see you next week.